Last section from chapter 3. So we're quickly approaching a chapter test for chapter 3. You'll notice we did a chapter test or a unit test before. It was 1 and 2. It was 5 sections, but chapter 3 standalone already has 5 sections. It's a very lengthy chapter compared to the other chapters in your book. So this is our 5th and last section for this chapter. We talked about enumeration systems in section 1, and then we've talked about addition, subtraction, multiplication, and now this is our last of our 4 standard operations, division. So division of whole numbers, and we'll start with a definition. For any whole numbers, a and b, where b is not 0, a divided by b equals c if and only if c is the unique whole number such that b times c is equal to a. A is called the dividend. It's the answer to the question. B is called the divisor. It's what you're dividing by. And C is called the quotient. Sorry, quotient is the answer. Dividend is what you're dividing. I said that backwards. A is the dividend, B is the divisor, and C is the quotient. And if I put numbers in, you're going to be like, oh, yeah, that's right. So why in the world is 6 divided by 2 equal to 3? Well, because equivalently, you can ask yourself, what is 2 times 3? And the answer is 6. Or you could say, what do I have to multiply by 2 to get 6? Right? It's the opposite of multiplication, an inverse operation. Okay? So there's a couple of models for, 4 models actually, for division, 3. They keep changing this particular part of the book, so it's 3 this time around. 3 models for division. The first one is called the repeated subtraction model. And the repeated subtraction model looks a lot like repeatedly subtracting the same value. And we're going to have an algorithm, this is the repeated subtraction algorithm later. They've changed the name of it, I think, to avoid the confusion, where it's a variation of this. So this is the idea is that Junie has 24 rocks and she's going to give them to 6 of her friends. How many rocks will each friend get? So imagine Junie has her 6 friends sitting in front of her and she goes, you get a rock and you get a rock and you get a rock. And she probably wouldn't even do that. She'd probably say, pick which rock you want, right? Like that's what she'd really do. And once she was done with the 6 friends, her 24 rocks, taking away the 6 would now be how many rocks? 18. And then she'd say, oh, we all get to pick another rock, right? And they all pick another rock, and they subtract off another 6 rocks. And they have 12 rocks left. And we keep doing the process until we either get to 0 or we get too few rocks for the number of people that we're trying to give them to in this scenario. So my writing's a little too big today. Now, that's the process, but what's the answer? Because that's the whole point, right? Is well, how many rocks did each friend get? Well, if you go back here and you count, there was 1 rock, 2 rocks that they got. Here's where they got rock number 3, and here's where they got rock number 4. The answer to the question is, how many times did I subtract 6? And the answer in this case is actually 4. It's 4 rocks. So it's kind of like the idea that if multiplication is repeated addition, then division is repeated subtraction. Okay? Any questions about that one? We're going to make this into a bigger scenario later. The next model is actually only written in one way in your book, but I bring it up as the alternate way for it because it comes up in proportional and statistical reasoning, and it's really nice for you to have seen it here once before it shows up again there. So there are 2 models that I'm calling the set model. One is a set partition model, and the other one says set partition variation. And what this actually has to do with how we're doing the division problem. And it's really the structure of the language that's different in the problems. So take a look at this. Junie has 24 rocks. She wants to give them to 6 of her friends. How many rocks will each friend get? That's the same question we had before. The other question is this one. Junie has 24 rocks. She bags them together in groups of 6. If she gives 1 bag to each friend, how many friends will receive a bag of rocks? So in one scenario, she gets to fix how many friends get the rocks. And in the other scenario, she gets to fix how many rocks each friend gets. Do Do you see the difference? So why does it matter? Well, the reason it ends up mattering is because later on when you get to chapter 7 and you're doing division, maybe it's even chapter 6 actually, doing division with fractions, it becomes a lot more difficult. When I talk about, 42 divided by 1/2, what does it mean to divide by 1/2? I can't make a group that's half big. Half big, what are you talking about? Like, it doesn't make sense, right? Like, how do I make half of a group? Well, it makes it a lot more sense if you talk about groups of size 1/2. So imagine you had 42 cookies, and you want to know how many halves of cookies you actually have. Well, I can do that. I can chop my cookies in half. I mean, I may eat 5 halves, but you know what I'm saying, right? Like, we can chop the cookies in half, and then it starts to make more sense about what it means to divide by a fraction. So that's why I present the 2 variations for doing this. And so in one situation, you're actually fixing the number of groups of something, and in the other situation, you're fixing the size of each group. And in fact, as a teacher, you have that same choice when you do group work with your kids in your classroom. You can either decide, right, like you've had people do this where they number it off, say, we're going to have 4 groups, so we're going to number off by 4s, and each of the, 1's going in this corner, 2's in this corner, 3's in 4, right? Y'all know what I'm talking about, right? And if I do that, what as the teacher I have done is I have told myself in advance, I'm going to have 4 groups when I'm done. The other option, which is the way that I do groups, says there's only so many people I want in each group. I only want 2 people per group or 3 people per group. So if I do it this way where I number people off into 4s, or that's not going to fix the numbers the way I want. And so what I do is I say, you 2 are going to be in a group, and you 2 are going to be in a group, and you 2 are going to be in a group, either in person, like I did the very first time I made groups for you guys, or electronically, which is what I did the last time, because I had to put your names into the spreadsheet and I paired people up. Okay? So what does this look like in terms of a picture? Well, this one says Junie has 24 rocks and she wants to give them to 6 of her friends. Well, what this means is that there's going to be, I'm going to put a box for each one of my friends, and I have to sort of put rocks in each of these boxes until all 24 rocks are gone, and I want to do that in an even way. So much like what I did with the repeated subtraction, I can do it, but I don't necessarily have to do it by 1 rock per person, but maybe I say, okay, well, maybe it's 3. So I'm going to put 3 rocks in each of these. Pardon the fact that all my rocks are different, but you know what? That's reality. Rocks are all different sizes, right? You bet. So, and I say, is that enough? Did everybody get the right number of rocks? You say 3, 6, 9, 12, 15, 18. That's only 18 rocks. I need some more rocks, right? Okay, well, let's just go back and add 1 more rock for each person. Well, let's check again. How many rocks does each friend have? Well, they've each got 4. 4, 8, 12, 16, 20, 24. That's it. I'm done. I've given away all 24 rocks. And then the answer would be that each friend got 4 rocks. Does that make sense? The other situation, though, says I'm going to create baskets or boxes or bags or whatever, and they're going to have 6 rocks in them. So here's my first bag, and I'm going to put in here 6 rocks. 1, 2, 3, 4, 5, 6. Well, I've still got some more rocks, so here's another bag. I've got 1, 2, 3, 4, 5, 6. That's not enough. I've got more rocks. So I'm going to make another one, and so I've got 1, 2, 3, 4, 5, 6. Still not enough space. I've got rocks left over. So my last basket finishes me out. 2, 3, 4, 5, 6. That's all 24 rocks. They've all been divvied up. But now the question is, how many friends or how many bags did I create for my friends? And the answer again is 4, right? But it's not 4 rocks in this case. It would be 4 bags or 4 friends, depending on how you're thinking about the question. But there's 4 groups. I end up with 4 groups in this way by fixing the number of, in this case, rocks per group. There is one more. This isn't. It's not a different descripting. It's a different model perspective, though. So this one's called the missing factor model. Junie has 24 rocks. She wants to give them to 6 of her friends. How many rocks will each friend get? So I mentioned early on in our definition of division the idea that if I want to have if what I want to do is I want to do 24 divided by 6 and get an answer, right? This is my goal, is that I could switch this around and make it in a multiplication problem instead. I could ask myself 6 times what is equal to 24? In other words, what is the missing factor here that makes this work? And of course, the missing factor is what? Yeah, it's 4. The missing factor is 4, so the answer would be 4 rocks. So instead of looking at it from more of a concrete picture form like we were in the last examples, we're looking at it more from a algebra point of view, which is fine too. So two of my kids are in 5th grade, and this is the kind of work that I see come home a lot of times is blanks. Or I'll see it come home like this. It's the beginning stages of algebra. I mean, I know what it is, right? And it'll say stuff like this. This is not the same problem, of course, but they'll do this and they'll ask you what is x. Their goal is not subtract 6 from both sides. Their goal is to figure out what's missing. What does that number have to be in that location for this to actually work and make sense? So it's the way that algebra is being taught these days is just from a different perspective earlier on and taught younger than you might have expected it to be. All right, so what I would normally do, for the sake of time we're not going to, is that I would normally have you guys get into groups and to create problems that do these types of different examples. And that's what I had you do on the videos. Hopefully when I said pause the video now and do this and come back, right? Same idea. I do want to give it a chance for us to have a little bit more that I talk about just for a couple more minutes before we close things off for today. But what I want you to recognize or to take away is this note. These types of models have less to do with the wording of the question, right? Multiplication, the wording of the question really fixed what model we were working with. These questions have more to do with the structure of how you create your answer, right? Do you subtract things off repeatedly? Do you draw the picture, or do you sort of have a missing place in your model where you're actually trying to fill in the blank with a multiplication fact? So that variation is something a little bit different. So let's talk about whole number division properties real quick, and then we'll stop for today. So if you'll remember back, multiplication and addition have a lot of really cool properties, a bunch of them in fact. And when we hit subtraction, everything failed. Right? None of it worked. And the reality is that the same kind of thing happens when we get to division. The properties, they start failing very quickly. And the first one is closure. So remember, if we're looking for ways that show something fail, we're looking for an example that shows it doesn't work. So in order for a closure property to not work, which it doesn't, the question is, what two numbers could I divide and end up with not a whole number? So can somebody give me an example? Two numbers divided that don't give me a whole number. 2 divided by 3, that would work. There's lots of examples, right? 2 divided by 3 is not a whole number. So it's not closed. Commutative property. No. Can somebody give me an example of the commutative property failing?
2 divided by 4, 4 divided by 3.
Okay, did I get them on there, Danielle, right? Okay, so 2 divided by 4 and 4 divided by 2 are not the same answer, right? They're not. This doesn't work, right? Did not hold. Associative property. The associative property also does not hold. I've got an example written down because this one's a little trickier to create, but there's lots of things you could create. So if I did 12, 4, and 2 as my numbers, you see that the attempt is to regroup the parentheses. So on the left-hand side, what's 12 divided by 4? 3. So I have 3 divided by 2 on the left. On the right, the part in the parentheses is 4 divided by 2. So what's 4 divided by 2? 2. Well, 12 divided by 2, that's nice. That's 6. But 3 divided by 2, whatever it isn't 6, right? It's not a whole number, but it's not 6. So these don't work either. The identity property. The identity property is the one that's like, we really wish it would work because it kind of works in one direction, right? We can say that the number 1 sort of stands a chance, right? Because, 7 divided by 1, that's 7. That's great. But it has to work in both directions, which is exactly when subtraction failed as well. 1 divided by 7 is not 7. So it's not the identity. And it's the only one that works because it's the only one that works halfway even, right? So it's not like I have to go check in to see if there's something else that might. it fails. Division by 0 is a royal bust. And the reason is because you cannot divide by 0, and I want to show you why. Because every now and then people get confused about whether you can divide by 0 or whether you can do the 0 divided by something. If you were able to actually give this a value, let's just call it x for the moment, the definition of division says that I would have to be able to multiply 0 times x and get back 2. There is no way to multiply 0 times anything and get back 2. Right? Because what's 0 times anything? 0. And it was a property of multiplication. So again, this doesn't work. I can't do that. And the distributive property, kind of like the identity property, works half the time as well. So here's an example of that. If I do 20 plus 10 divided by 5, and then I do 20 divided by 5 plus 10 divided by 5. It actually works. 20 plus 10 is 30. What is 30 divided by 5? 6. Yay! 20 divided by 5 is 4, and 10 divided by 5 is 2. So like these work. It works, but it only works in that order. If I do the distributive property in the opposite order, like this, if I try to do 20 divided by 10 plus 5, right? The grouping's in the addition instead of the grouping the other direction. Like this. This will not equal 20 divided by 10. I'm running out of space. All right, so here this would end up being 20 divided by 15, which is not a whole number. But on the right-hand side, I would get 2 and 4, right? And these do not work. The non-whole number on the left does not equal the whole number 6 on the right. All right, so we will pick back up next time with algorithms for division.